In the previous section, we learned how to use the derivative, okay, to see the increasingness and then decreasingness of the function. In this session, we're gonna, okay, move forward the discussion, okay, to the extremum points, which is also related with the increasing or the decreasing. If you look at this graph, right, when you have, right, the decreasing and then increasing function of a part of your function, right, there will be always, right, a point, right, which you turn your function, right, from increasing to the decreasing. Okay, those are the points, right, which we know, right, they are the critical points as well, but they are also, as you see, right, either the maximum or the minimum points, correct? But we need to give, right, the exact definition what we mean by maximum and the minimum, right, with the formal math definition. Yes, when you look at the graph, you can just easily say this is the right maximum or the minimum, but if you don't have any graph, you don't have any chance to say that. That is why when I look at this graph, first of all, right, without using the derivative, can I say something about the, right, the maximum being maximum? As you see, if you try to observe, okay, what's going on around the sea, so let's try to take, right, some value around the sea, any value, any open interval. Let's take an interval here, open. There are some reason being open, right? We are not gonna get into that part. So if you have any interval around the sea, as you see, whatever x value you got here, those values, right, those values f, right, will be less than of your f of c value, correct? Yes, all of the x values, right, the f of x values will be less than the f of c values. So I can just definitely say, if you have the maximum point, right, the maximum point, so whatever x value you take, right, around in this interval, around this interval, which you say, right, this interval, look at that, since this is the interval AB, which includes C, all the, right, the x value you take here will be less than f of C. Of course, C also belongs to AB. If you can find, right, that type of C, we are going to call this one the relative maximum. Why we call the relative maximum? Soon we are going to discuss about that. So what about the D? Can I say the similar things about the D? Yes. If you look at, right, around D, there is no value which is less than the D, right? As you see, if you look at the f of t is the smallest value you can take in this interval. There is no value around you can find which is less than f of t. So minimum, right? Take the x value in this interval. Let's say this is also AB, and then d is in this interval again, right? So now all the f of x value should be bigger than f of t. That is why it is minimum. But of course you can find out, right, another maximum somewhere, right? Since these are just one maximum and the minimum. If you look at, okay, if I increase more, right, I'll look at that. There is another maximum here, which is, right, bigger than this maximum. That is why, okay, we're gonna call this one that is the relative maximum. This is the, right, the absolute maximum, since it is bigger than, right, all other maximum around, guys. That is why in this lesson we are just gonna give, right, the relative maximum or the relative minimum definition, since you can find out, right, some other maximum which is bigger than all other maximum or the minimum in the same manner. Okay, these are the relative maximum and the minimum definition. I gave it to you, but still I'd like to use the derivative, right? Derivative to see, since the derivative will make my job easier, okay, when I search the maximum or the minimum point, since these definitions still is not useful, okay, if you want to use, right, these definition with just the formal definition of function, it's just not going to be easy. That is why I like to relate this idea, okay, with the derivative. Okay, if you look at, right, the f of c point, around f of c, I know that now my function is increasing and then decreasing. So I have a test right for the increasing and then decreasing. As you see, my function derivative is less than 0 on this part, and then my function derivative is bigger than 0 on this part. And then you can say the similar things for the d point, guys. Okay, what's going on here, if you see that if my derivative, right, the change sign, right, at this point, as you see, at this point my derivative change sign, then I can say that I have either maximum or minimum. When I can say I have maximum, if it goes right from positive to negative, I have maximum. If it goes to negative to positive, right, then I'm gonna have the minimum point. Now it is time to give this test so that I can use, right, the first derivative test we are gonna call to figure out the right external points, guys. So let's summarize, okay, what we talked about the maximum minimum points in this test. We are gonna call it the first derivative test, guys, okay? And then since we are gonna have the second derivative test, right, as this title implies, so you have the right number, which is C in this case, right? And then I know that's gonna be the critical point. What does that mean? If your derivative is equal 0 or it doesn't exist, right, we call it the critical point. If you have the critical point in this interval, and then you just need to look at the derivative of your function around that point. You see, if the derivative of your function positive, right, in this interval, and then negative, right, in this interval, so you are going to say that your function will have the relative maximum at that f of c, correct? That's the maximumness. But, right, if the case is other way around, what we mean, right, we are going to say that we have the f of c is relative minimum when you have, right, the f prime x is negative on this interval, but it is positive, right, on this interval, right, then I'm just gonna say that this is gonna be my relative minimum, guys. So that's the first derivative test. Now let's apply this test, right, to the function to see if where I have the minimum or the maximum using the derivative, guys. Let's look at this example. What I should do, right, I should take first the derivative of this function. As you know, it is just a powerful rule application, which is 8x minus 16. What I should do, I should make this one 0. If it is 0, 8x minus 16, which is 0, and then x is going to be equal to, okay, this is my, right, the what? Critical point, since it makes the, right, the derivative 0. What I will do, I will just draw such a diagram to see, okay, where my function derivative is 0 or the positive or negative. I know, right, at here it is going to be 0. If I use, right, the sum value bigger than 2, which makes, right, this positive. So if you use, right, a value bigger than 2, those values will make your function derivative positive. But if you use, right, the sum value less than 2, they will make, right, your function derivative less than 0. So in this interval, my derivative is going to be negative. In this interval, my function is going to be positive. So let me use, right, my first derivative test. What it was saying this: if your function derivative is negative on, right, on this part and then positive on this part, you have, right, absolutely you have a maximum or the minimum point. Okay, but first of all, I need to combine this test by the other test, so that I'm going to show you a nice thing. Remember the, right, increasing or the decreasing we discussed before this first derivative test. It was saying if your function derivative is less than negative, your function is decreasing, right? If your function is, right, the derivative is positive, your function is increasing on that part. I'll look at that. If you look at this shape, right, here you have a, right, you have a volley. That means, right, you have absolutely, you have a minimum point. Of course, there's a relative minimum or the absolute maximum or the absolute minimum or the relativeness or the absoluteness. Okay, we don't discuss. I just use absolutely, okay, you have, definitely you have a minimum or the maximum. But look at the first derivative test says the same thing, right? Since you have, right, a changing point, your derivative, right, they change the sign from negative to the positive. That's why, okay, you have the minimum point at that point. If you draw the graph of this function, of course, you are gonna absolutely see, okay, you have a, right, the minimum point at x equal 2. But without drawing the graph, look at it, I'm able to see, okay, where I have the minimum or the maximum. Is there any other minimum or the maximum? No, since we know the quadratic function, they just have one minimum or the maximum point, as you know. Now it is time to apply the derivative test, right, to the real world problem. Look at this problem. This is the function, right? We can model the female moose and their masses, right? So if you would like to know, okay, when they're gonna have the maximum weight, what time you can hunt them, right? So you can just, right, to take the derivative of this function, which is exponential function, and then we know, right, how to take their derivatives. Of course, you have, right, the polynomial here, that's why you need to apply the product rule, right? The product rule. If you apply the product rule, then what you should do, you should find the critical points, which you need to make this derivative function 0, and the 4.96 is going to be your critical point. What you should do, right, from the first derivative, we know that. We need to check it out if, right, my function derivative is positive around this one. As you see, if you use, right, the m prime 4 is going to be bigger than 0, but m prime 5, which is bigger than 4.96, is going to be less than 0. That means, that shows me, right, this point is going to be the maximum point for the function. So if it is maximum, I can plug that point into my function to figure out, right, after this year, right, at this time, how much, right, I can have, I can get some meat from this female moose. As you see, right, after 4.96 years, right, this moose will have the, right, 485 pound weight they will have. Second example is from the market. So let's say, okay, you just sell the telephones, right, and then you know the demand function in the market, and to calculate the revenue, you need to multiply the demand by the price, right, so that you can calculate the revenue. This is my revenue function. If I multiply the demand by the revenue, this is gonna be my revenue function. So if I would like to find out the maximum revenue, okay, when I can make the maximum revenue, as you know, you need to write take the derivative and then find the critical point. So after doing that, as you see, this is just the product rule application again. Q is going to be equal to 10. That's my critical point. I need to check out, right, if I have the maximum around, right, this point, using the first derivative test. Look at the take a value less than 10, which is 9, and then if you plug that number into the derivative, which is going to be bigger than 0, and then take another value which is bigger than 10, which is 11, look at that, the derivative is going to be less than 0. So I got it right. A value, around that value, I had, right, the positive and the negative derivative. That I can say that this is going to be, right, the maximum point, since it changed from positive to negative, as you see. And then if I use, right, that value to calculate my demand or the revenue, of course, right, the demand function will give me, right, this value. So I can get that, right, if I sold my phones, right, $73, so I can get the maximum revenue, and then you can just calculate, right, how many phones you can sell at that price to get the maximum revenue, guys.